Hey everyone, this is video 258, magnetic field of a solenoid. Let's start off this video with a question. A crane in a junkyard can carry large amounts of scrap steel, right? How is it that this part here can carry all of that weight? What do you think it is? Please put your thoughts in the comments below. Let's take a look. A solenoid is a long coil of wire with the same current passing through each loop, also called a turn. So in a previous video, we just talked about a loop of wire producing a strong magnetic field. Now we're saying, well, if you have a bunch of loops of wire, that's called a solenoid, and that's going to produce an even stronger magnetic field at the center because the field due to each single loop is going to combine. So what we have here is the expression for the magnetic field due to a solenoid, and this is going to be the field inside the solenoid. The equation is B equals mu naught, the permeability of free space, times N, the number of turns or loops, times I, the current, and L is the length of the solenoid. So even though it's turned into a bunch of loops, it still has a certain length. So let's take a look at some questions. Oh, wait, I have a note here. The field does not depend on the radius of the solenoid. So we don't derive the equation, we do just have to accept it, but you can see that the radius of the solenoid does not matter. All that matters is the length, the current, and the number of turns. Let's take a look at the first question here. It says solenoid 2 has twice the diameter, twice the length, twice as many turns as solenoid 1. How does the field B2, the center of 2, compare to B1 and the center of 1? So this is one of those questions where we're doubling a quantity. What happens to the other quantity? So the first step is to write down the equation for the field inside a solenoid. B equals mu N I over L. Now let's see what variables that we're changing. We are changing the diameter, but the diameter doesn't matter, so that doesn't even matter. We're changing the length, and we're changing the number of turns. So this would be B1, and say N1 and I1 and L1. B2 is going to have twice the number of turns, it's going to have 2 N1s. It's going to have the same current, but it's also going to have twice the length, 2L1. So what happens? Well, the 2's cancel out, and you end up with the exact same field as number 1. So the answer is C. It's just a matter of plugging in each variable, seeing what happens to each one, and then doing some algebra to see what it simplifies down to. Let's look at another question. What is the direction of the current in the solenoid as viewed from the top? So, which way is the magnetic field produced by a solenoid? We're going to use right-hand rule number 3. It's the same thing as the field produced by one loop, because it's just a bunch of loops that combine to have a stronger field. So remember, right-hand rule number 3 told us that if we curl our fingers in the direction of the current, then the thumb is the magnetic field within that loop. So in this case, the upward arrow here is the magnetic field that is produced by the solenoid. So we want to know which way is the current. So go ahead and try it out on your own. And now let's take a look. We must curl the fingers this way so that the thumb is up. So we must curl the fingers this way. If you viewed it from above, it would be counterclockwise. So you can see that the current in the back here is going to the left, and then as it goes to the front, it's going to the right. So do the same thing with your right hand and curling that left hand around it. So in the back, the fingers are looping to the left, and in the front, they are looping to the right. So if you keep following that, in the front, they are looping to the right. The back, they were looping to the left. So your fingers curling this way corresponds to a current direction as shown here, where as viewed from the top, you can see, if you just bring your hand lower and just look at it from the top as you're curling your fingers, that's a counterclockwise direction. So hopefully you can see that counterclockwise direction. Since this is a short video, we can add also the example for this video. It's a plug and chug, the magnetic field of a solenoid. It is a pretty cool application because our MRIs have these solenoids. So a typical MRI solenoid has a length of about 1 meter, that's the length, diameter of about 1 meter. We don't care about the diameter, right? A typical field inside such a solenoid is about 1 Tesla, that's the field. How many turns of wire must a solenoid have to produce this field if the largest current the wire can carry is 100 amps? So that's a good point, right? The field of the solenoid depends on the current, right, as well as the other variables. So you might think, well, if I want a strong field, can I just make the current super strong? But you can only make the current so strong because a wire can only handle so much current. Too much current could cause the wire to melt. So this is a plug and chug where we have the equation for the field inside a solenoid, and we're looking for N, which is the number of turns. So we're going to solve for N. It's going to give us B times L over mu and I on the denominator. And then just plug in all of our values. B is 1. L is 1. That's pretty easy. Mu is 4 pi times 10 to negative 7. And I was 100. So plug in all of those numbers, and that's going to give us 8,000 turns. So that is totally realistic that in order to get a strong magnetic field, you're going to have a lot of turns. One more thing, back to the question I had at the beginning of the video, right? When you have a solenoid and you have that current going through all of those loops producing a very strong magnetic field, do you know what that's called? That's actually called an electromagnet. So I didn't have it in one of my slides, but if you've heard of electromagnets, right, these are magnets created by electricity. Your loop of wire has a current, and that's producing the magnetic field. So I'll leave you with that. I'll see you in the next video.